Alright. Hello and welcome everyone to the second session of the RL workshop day 1. So in this session, we will give you a flavor of how you can run your own RL algorithms. So we have a bunch of 4 brilliant students from IISc who will be giving you demonstrations of different algorithms that you must have either heard beforehand or some of which you must have heard in Professor Vidyasagar's talk. Right? So they will show you when you try to run these algorithms in practice, what are the challenges that you face, right? And what do you expect when you run these algorithms and so on and so forth. So the first speaker for today is Vamshi, and you can take it.
Hello. Keep it here only.
Okay.
Okay.
Welcome back, everybody. So today I'll be talking about tabular queue learning. So just to refresh the things that are from the morning session. So in the reinforcement learning, we have this agent environment interface. Agent is a decision maker which interacts with the environment, and it gets a snapshot of the current state, which is called ST. So based on the current state, it will take an action, which is AT, and environment responds by going into the next state, which is ST plus 1, and it also gives a reward called RT plus 1, which is a scalar value. So here the goal of the agent is to maximize the cumulative reward that it can accumulate over the long term. So we don't tell the agent explicitly what actions to take and what not to take. On the other hand, agent has to try out various actions and then figure out what is good in the long run. That is the goal of the agent. So Markov decision process is a mathematical framework that captures this agent environment interaction. So as you have seen in the morning session, it has this state space which consists of all the possible states an agent can be in, and an action space where agent can take all these multiple actions, and then also transition probabilities, which indicate if you are in a particular state and take an action, where can you possibly go and with what probability. And you also have a reward function and a discount factor. So discount factor is basically indicates how far-sighted or near-sighted the agent is. If the gamma value is close to 1, you care more about the future rewards than immediate rewards, and if it is close to 0, you only care about the immediate rewards. So here is a simple example which we call it as grid world. It's one of the simplest examples of Markov decision process. So here you can see a grid which is divided into cells. So there are total of 36 cells here. So each state here, each cell represents a state here. For example, here the first cell in the topmost and left is a 0, 0 cell. That is the index of the cell, and it represents a state. And in each state there are 4 actions available, which is up, down, left and right. So there are total of 36 cells and 4 actions in each state. And also to make things look interesting, we will add some special states called error states and goal states. So if you look at these cells marked with X, you can think of them are like obstacles or traps which we want to avoid, because if we go into these states, we'll get some negative reward. On the other hand, if we go to the states marked with O, which are green in color, we will get a positive reward. And any other state which is white in color, we call them empty states. So if you go into those states, we get a reward of -1. This is just an MDP with a reward that is made up. Obviously, you can change the size of the grid. You can mark whichever the cells you want as error states and goal states. So this is what I've represented here. So you can also think of it as like a auditorium where a robot is present at any given cell, and you want to reach the goal states by avoiding the obstacles. You can think of it like that. So also we assume that the environment is deterministic, which means if you take an action left in any given cell, you will go to left with probability 1. There is no noise or any stochasticity. So for example, if you are in the cell 0 and 5, and if you take an action down, you will go to the cell which is 1 and 5, and if you take action left, you will go to the state 0 and 4. On the other hand, we want to encourage, we want to make sure that the agent is always remains in the grid. So if you are in the state 0 and 5, and if you take an action which is up or which is right, which might take the agent to go right, we will manually say that the next state agent will stay here itself. But since it was trying to go out of the grid, it will incur a negative reward. So we are giving a negative reward of -2. So whatever I said right now, you can, I don't know if the link is up yet. Okay, soon this link will be shared with you and you can execute the cells and see how it behaves. Okay. Okay.
Reload the page.
Yeah. So
Yeah. 1 minute, 1 minute. Sorry.
yeah. Fine. Yeah. So you guys can go to this link and copy this collab file onto your local drive and execute each cell so that you can see what is the output of each cell. So I'll be ignoring the code in this first part of the cell, which is just a visualization purposes. So in the second cell, there is a class called grid world, and it takes the dimensions, goal states and error states as input. So based on the number of dimensions you give, this grid world can be made. So here we are looking at a 5 by 5 size grid, and the goal states are marked, which are marked here. So size is 5, so 0 and 4, and 1 and 4, and 4 and 0 are the goal states, and these diagonal ones are marked as error states. And also you can see that in the step function, which will basically define the transition probabilities, I have some special states called terminal states. Pay there and it will receive a reward of 0. So that we are writing it here. So if it is a finite horizon, the flag is on, and if the current state is in one of the goal states, which we also make it terminal states here. So agent will still, the next state will be still the same as current state, and it will receive a reward of 0. And these two lines indicate that if you are trying to go out of the grid, you will stay there, but you will receive a reward of -2. So if you take an action up when you are in the topmost row, or if you take an action down when you are in the bottom row, you will still stay there, but you will get a -2 reward. Same thing, if you are in the leftmost column and trying to go left, or rightmost column and trying to go right, you will get a reward of -2. If any of these things doesn't happen, then normally if you move left, you will go left and you will go right, and so on, based on the current state you are in. And also you will receive a special rewards. If you go into a goal state, you will get a reward of +5, and otherwise you will get a reward of -2. So this is the basic MDP structure that we are considering now. It has discrete states and discrete actions. You might have learned about Q-learning in the morning session. So in Q-learning, we are trying to directly learn the optimal Q function in an iterative fashion. So we start with a Q table which is initialized with all zeros, and then we start with some cell, we take an action and we observe the reward and we go into the next state. Once we go into the next state, we get these state action pairs, and we use the update rule, which is given by this Q of S comma A equal to all this. So in this, we know everything on the right hand side of the equation. So we know the current Q values, and we know the gamma, and we know the step size alpha, and we also know the next state and the immediate reward. So we can execute this after one state transition, and this is coded here. So you can see in this part of the code that that is exactly represented. So now first let's look at a finite horizon setting, where once we reach the goal state, the transitions end. So as you can see here, if you start below the diagonal line, you will try to reach the goal state which is nearest, because every other transition you make will incur your negative cost, and there is only a positive reward here. Every other cell will give you a negative reward of -1. So the best thing to do is go to the goal state as soon as possible, because you have a finite time. Otherwise, you will keep on incurring the negative rewards. And if you start above the diagonal line, you will reach one of these two goal states, because that is the quickest way to get the positive rewards. And there are some cells here where you can take any two actions and they will still give you the same optimal action. So from here you can see that there is only one optimal Q function, but there are multiple optimal policies which gives the same Q function. For example, if you take this cell, even if you go right, you can take either right and up, or you can either take up and two rights. You will still get there with the same cost. So this is happening because of symmetry here. So you can see the same here. If you are here, you can either take one down and two lefts, or two lefts and one down. It doesn't basically matter. So there is one optimal Q function and then multiple optimal Q policies. On the other hand, if you go for the infinite horizon setting, where even if you go to the goal state, the episode will not end. You will still have to keep on taking the actions and incur the rewards or the costs. So that is given in the next, you can execute the cells yourself, and you will see these values changing. So here you can see a different behavior, because in the long run you don't care about the immediate gains. So wherever you start, the agent is trying to go to the topmost cells, because if you go down, once you go here, even if you reach the goal state here, the next action that you take will take you out of this cell and you will incur a negative reward, which is not good in the long term. But so the agent prefers to go here even if it takes a longer time, because once you go into one of these two states, you can jump around from one goal state to the other goal state, and you will keep on getting a reward of +5. So that way the agent prefers to go here. So I hope you can see how the things change for the same grid world in the finite horizon and infinite horizon. The agent has automatically figured out which is the best way to go, where is the best way to go, based on the settings, which is gamma and terminal states. So any doubts here till now? Like, this is one part of the session. So next I'll be talking about Q-learning in some other environment called Cartpole. Yeah.
So there is nothing stochastic in this setup, right?
No.
So is this the optimal way to solve, or are there more efficient ways to solve this kind of a problem over and above Q-learning?
I think you can directly calculate the costs and then take a decision instead of going for the Q-learning. I think this is the best, not best way, but if you have, if the agent is stochastic, then maybe Q-learning would be better in that case. So I'll be talking. Yeah.
So will the agent take the same action again and again to get the reward continuously, like moving between two cells because you get it?
Yeah, that is what exactly is happening in this infinite horizon setting. Because the episode doesn't end and there are no terminal states, the agent has to take an action and move to some other cell. So it prefers to go to the next goal state rather than somewhere else. So these two goal states will become optimal than this one, which is at the bottom. So agent prefers to go there. If it goes here, it might incur negative reward after the year, because it has to move out of it eventually. So yeah. Oh, okay. I skipped a part, which is there is an epsilon here. We talk of, I don't know if you know about the epsilon greedy policies. So sometimes to encourage exploration, so Q learning is basically a value iteration, which means we represent the optimal policy in terms of optimal Q function. So from there you can directly get the optimal function. So So you can take any actions while exploring, but what we choose to do is we want to take an actions that are greedy with respect to the current queue function, but with some exploration probability we want to take some other actions, because there is always this exploration versus exploitation trade-off. Because if you to perform the best, you need to take the actions which you already know are best, but to discover such actions you need to try new actions. So with 0.2 probability, which means 20% of the time the agent takes random actions, and 80% of the times it exploits the actions which it already know is very good.
How do you know the balance is optimal between exploration and exploitation?
Usually we choose very less exploration when we can choose to explore more at the start, because the Q values are not very good, but over the time we can decrease the exploration and improve the exploitation. That could be one strategy.
It's like random, means we need to experiment, or do we have any guideline that
There is no guidelines, but
there are 5,000 iterations?
yeah.
So it's like up to 2,500 you will be following. I'm just giving an
Yeah, okay.
Up to 2,500 you are going to explore,
Okay.
and then remaining 2,500 it will follow exploitation.
We can do that, but the more smooth way to do is always explore, but with less probability you do that. Like initially maybe you choose 80 to explore 80% of the time. As the iterations progress, you slowly decrease it to 20% or 10% as the Q values keep getting better and better. That could be one strategy.
To experiment, then we decide, or do we have any guidelines in general?
In general, I think people follow the heuristics, which is like start with high exploration and then decrease it over the time according to some scheduling.
It's like this curve and this.
Yeah, some curve which goes down to 0 eventually. Yeah. Okay, so you need to give the reward function. So you will have a task in mind. So you need to give a reward such that if you optimize the reward in the long term, the task will be achieved. So in the next one, I'll be talking about a example which is called Cartpole. Any more questions? No? So if the reward is not designed properly, and if the agent is trying to maximize that reward, but the task is not achieved, that's not a good reward. So by maximizing the reward, if the task can be achieved, that will be considered as a good reward. Next, I'll be talking about this Cartpole environment, which is one of the very basics and standard benchmarks in reinforcement learning and control algorithms. So here the setting is that there is a cart which can move in one dimensions, either to the left or to the right, and there is a pole mounted on it vertically. So now the objective is very simple. We need to apply the forces or move the cart either to the left or to the right, such that the pole always stays near that vertical. So we basically need to balance it near the vertical for as long as possible. So here the state is represented by 4 variables, which is the cart position x, cart velocity x dot, and angle from the vertical, pole angle from the vertical, which is theta, and the angular velocity of the pole, which is theta dot. And all these variables are continuous variables, so they are not discrete. But the actions are discrete, which means you can either move to the left or to the right. So to find an optimal function here, this is a bit challenging problem, because if you apply random forces, the pole will immediately lose balance, and once it crosses certain threshold, the gravity will take over and it will be difficult to control. So you basically have to control it very minutely when the pole is within certain threshold from this vertical. So if we want to apply Q-learning to this setting, we cannot directly apply, because here the state space is continuous, and to represent something in a Q table we need discrete states and actions. So one idea is to discretize the state space. So right now we have 4 state variables. So we can choose to discretize them. So how do we discretize usually? So if one of the state variables is taking a value which is in the range from -10 to 10, and if you decide to go with 2 bins, so from -10 to 0 you call it one bin, and 0 to 10 you call it another bin. So if the value is, let's say, 5.5, which falls into the second bin, 0 to 10, so you represent it as state number 1. If it falls into the other one, you represent it with state 0. So now we have to do this for all the state variables. Like let's say now there are 4 state variables, and we decided to go with 2 bins for each of the state variables. So there will be a total of 2 power 4, 16 states, and each bin, state will be represented using 2 bin numbers, using 4 bin numbers, one for each state dimension. And here the reward is very simple. If at any given time, if the pole hasn't fallen from the vertical, you will receive a reward of +1, and if it has fallen off, you will receive a reward of 0. And let's say the episode lasts for 500 time steps. The maximum reward you can achieve over 500 time step, if you do the good job, is 500. Otherwise, you will receive something in between.
I have a question here.
Yeah.
So you said, like, beyond a threshold, when if it crosses, like, the gravitational force takes over and difficult to. So are we getting into a rule-based rather than an oral-based?
No. Like, I am not saying that there is a particular thing, actual thing we know. Gravity is always affecting even when you are near the vertical. But like there is a certain threshold after which it becomes very difficult to control. Okay. So that's what I am saying. So it's like.
Should we teach the agent to know about this, or will it self-learn? That?
It should figure out itself, because we are talking about model-free algorithms.
Okay.
It should try out various actions and figure out that I should not do this or I should do this.
The threshold should be learned by the agent himself, and we won't be hard coding.
Yeah, we are not hard coding, but if you go to the Cartpole environment, in the gym environment, they have put a threshold of 12 degrees from the vertical, I think. Okay. After which the episode ends. So even if you want to achieve, there is no more control to do. So you cannot get positive reward. So it has to try to put the pole within this 12 degrees either side. Otherwise the episode ends and you will not get any more reward.
Thanks.
Yeah. So here I will try. Here is a code that can discretize the bins. So you will be given a state and the bins, and based on the bin values, just like I said earlier, -10, 0 and 10. Those are called the bin edges. So if it is from -10 to 0, you will put it in that bin. Anything left to -10 will also fall into that bin. So and here is the choose action. So how do you do the exploration? So you will generate a random number which is between 0 and 1. If the number is less than epsilon, let's say epsilon is 0.1, so you will be taking an action randomly, which means 10% of the times you will be acting randomly. And if it is not the case, which is with 90% of the probability, you are taking an action which is greedy with respect to the current queue function. You can see this np.argmax here. And then in the update queue function, you just have this target and the error and the update rule here. So let's start with 2 bins. Yeah. So let's start with 2 bins and see how the agent performs. So I'm running the experiment with a maximum of 5000 episodes and 2 bins. Here you can see the reward that is achieved over the iterations.
State space is a vector, right?
Yes, it's a vector of 4 dimensions. Yes.
Well, it is done for each,
Each dimension, yes. So there are 2 bins and 4 state dimensions, so there are 16 states, and for each state there are 2 actions available, so the queue table size will be 32 here. And let's do it with the 4. So we got an average reward of 69 over 10 episodes with 2 bins.
This code is not saved in this, right?
I'm not sure if it is saved yet. Okay. So with the 4 bins, we got a reward of 131. So the idea here is it is taking some time to run. What? Yeah, so you have a you have a queue table and you have entries in each of the queue table. Now you can at each iteration you can basically compare the norm difference with the queue table, and if it converges, which means it will be the difference will be very low. So that could be used as a stopping criteria. Or sometimes you can use some fixed number of iterations and hope that it will converge. So as you can see, as the number of bins increases, when the number of bins is very less, agent has a limited understanding of the state space, so it cannot exploit the state space rewards properly, and the agent the policy that we get will be suboptimal. But as the number of bins increases, the agent will get a very good understanding of the state space, and the reward increases up till some point of the time. But if we keep on increasing the bins, what happens is that we could run into some problems, because first thing is that as the number of bins increases, the queue table size explodes. So if we take 2 bins per state, then we have 32 queue table size. On the other hand, if we move to 10 bins, which is 10 power 4 times 2, which is 20,000, so the queue table size explodes. So as the queue table size explodes, to get the same performance, we need to run the algorithm for long time, because we need to visit each state action pair multiple times to make sure that the queue learning algorithm converges. So also within a finite number of episodes, it could be possible that some state action pairs may never be visited, or they will be visited very less frequently, which means some of the queue values will be bad or very poorly updated, which can lead to unreliable policies. And the second thing is the generalization issue. So as the grids become finer and finer, agent will learn very specific details about the state space. It won't be able to generalize well. Assume there are 2 states which are very close, but they fall into different bins. The agent won't be able to take advantage of such states and generalize well. This is equivalent to overfitting in supervised learning. So intuitively we might think that as the number of bins become more, the performance might get better, but we run into these problems that convergence will be delayed and the memory requirements grow too much, and generalization may not be very well. So we might need to resort to some kind of function approximators, which is basically neural networks. So that will be discussed in the next section.
If some few values are visited most often,
So
way to promote that.
so basically, when you are in some state and you are taking an action, that action will decide where you are going visiting the next state. So it depends on the states.
Say 50,000 states, and some of the QSA pairs are not visited often enough. Is there a way we can tell the algorithm to do that? Is there a way to do it?
I think you can maintain the visitation frequency for each of the state action pair, and whichever the ones are visited very less, you can start your agent in that states and execute random actions and increase the probability of the probability of visiting that state action pair.
Is it commonly done?
No, I think this DQN is very much limited to discrete spaces or in the grid world setting. As we go into the, like let's say here we had only 4 states, 4 state dimension, and if you use 10 bins, the memory requirement grown to 20,000, right? But if you have in the real world robots or something, maybe if you have 40-50 state dimension, if you have to use 10, that will be infeasible, 10 power 50 or so. So we usually go to policy gradient or other algorithms which can handle the continuous state spaces.
But if you go to multi-state spaces, we've got infinite state action based.
So we will not discretize there. We will directly train a network which can take advantage of how generalization, like if two states are very close, maybe the optimal action should also be a little bit closer, that kind of setting. Yeah. Yeah.
In the environment, there will be a friction between sliding contact, right?
I think the assumption here is that there is no friction.
If we add a friction
Yes.
and try to use the same learning policy in that environment, can we transfer that knowledge, like transfer learning in supervised kind of something?
Maybe you can start with the Q function that you already got, and you can start the iteration from there. Maybe it will converge sooner.
Okay, means there are fine tuning something like that.
No, I am just saying like you already have a Q network which works very well for the frictionless one, and if you go for the friction one, you can warm start the next Q table with the Q table that you already got, and from there maybe it will take less number of iterations to get there.
Is it possible to use the Q learning algorithm without here?
Yeah.
Without binning the data, like without using the bins. So you whatever state action pair you have encountered in the episodes,
Yeah.
you save a Q value for each of them.
That
and
is
then try
actually.
to fit a,
Yeah, but like if you take the state as it is, you might not go there next time. Like
yeah, but you will visit some of the other local states, right?
yeah,
Neighboring
so
states.
you need to have some idea of like what is that local, which is where the discretization come into picture. Like if you visit even in the neighboring state, you consider that I am basically visiting this bin. Otherwise, you will go to some state and then you will never visit that state again.
But can we like consider it as a continuous function instead of?
Yeah, you can consider, and that is the next tutorial, where how to make this Q-learning scalable to continuous spaces. Instead of maintaining a table, you are maintaining a Q network, which can do that.
Okay.
Yeah.
Initialization strategies or always start with 0?
0 is just to be on the safe side, so nothing more. You can start anywhere, I think. So since we are designing the reward, we know what is the expected. Like since 0 and 1, you will not get negative rewards. So you can start at 0 or some 1.
So we'll move on to the second speaker now, but before we do that, a quick announcement. Whenever you have a question, please speak into the mic. As you are aware, this session is being broadcasted on YouTube, right? So if you speak without speaking through the mic, your question won't be audible, and then the audience wouldn't know what the context is. with regards to what the question is, I mean, what answer the speaker is giving. That is the first request. The second thing is, we are sorry we couldn't put the links up beforehand, but now all the links are there. If you go to the RL workshop webpage, there is a tab on the webpage called simulation links. If you click that, you should have all these links up. So in case you have missed seeing this Q-learning Cartpole thing that Vamshi was discussing, you can actually go now and click on that link and get a feel for what was being discussed. Thank you.
Lakshmi, how was it?
Nice.
Okay, na?
Yeah, it was nice.
Hello. Am I audible?
Oh, sorry. Forgot.
Hello. Okay, so I guess Vamshi has now motivated you like why do we need function approximators. So before going into the Q-learning algorithms for continuous state spaces, I'll briefly cover how you can code it up in a neural network library called PyTorch. So if you can go to the web page on the events at the bottom, you'll find this collab function approximators in PyTorch. Please open that. So you can create a copy of this in your drive. And at the top, I have given some useful external resources that you can refer to for going in depth, because I'll cover this at a very high level only for you to understand DQN, and that's it. So if you want to understand how you can use different types of architectures or optimizers, or understand some of the formal approaches that are there behind this approach of function of approximators, you can go to these links. So anyways, neural networks are basically simply like some function approximators where you are trying to optimize these weights W, biases B, and sometimes depending on the architecture you might have something like a hidden state or some convolution kernels, etc. And using these the class of functions, you can try to learn very complex and non-linear this functions. So for example, you like in the previous case, the Cartpole had to learn a Q table, right, for the state space which is continuous. So as you saw that the memory was exploding as you increase the number of bins. Instead here what you can do is you parameterize the Q table using a neural network and try to learn that non-linear function of given a state and an action, what would be the Q value, that is the expected sum of rewards. And there is some terminologies like what's been given here, like weights, biases, and activations, which I'll cover them in the as an example below. So typically whenever you Google or refer to any resources online, you will see a picture like this where you have some input layer, some hidden layers, and an output layer. So what that basic mathematically means is that you have a vector x input. In our context, it could be the state which is continuous, and then you have a hidden layer h1 here, which is simply a function g1 of w1 x plus b. So w1 is the weight of the first layer and the bias at the first layer. So the inside G, you can see it's simply a linear transformation, Wx plus B, and then you pass it through G, which is generally some non-linear function to capture these non-linearities. So like for example, sigmoid or tanh or rectified linear units, ReLU. And then in the second layer, you again have H2, which takes the previous hidden vector. So I think there is a typo here, it should be G2. So G2 of W2 times H1 plus B2. And then in the final layer you have again like Y is equal to GY, WY, H2 plus BY. So overall neural networks are nothing but just function compositions of these linear transformations passed through these nonlinear activations. And the parameters of the network here in this case are simply this W and B. So this type of architecture is commonly known as an MLP, multi-layer perceptron. So is everybody clear till here? Any doubts? Okay. So for an example, I'll cover how you can sort of use a neural network to fit a circle. So basically, you learn the function of a circle. So given an angle, and from 0 to pi or whatever, and you should be able to predict where the point will lie on the circle. So basically, r sine theta, comma r cos theta. So we'll predict two quantities. So this cell is only for generating the data for our problems, this regression problem. So you can run this cell, and it will generate this sort of a circle with some noisy points. So I've added this to make it not overfit to just circle, but some general pattern that is there in the data. So writing the neural network in this library PyTorch. So typically you would write your neural network as this class here. I'll called model, and you'll simply call the base base constructor of this nn.module, and then here I'm defining something called as nn.sequential. So what this basically means is that this is simply defining my operators that I want sequentially. So first I want something called linear, nn.linear, which is simply wx plus b. So I'll get a vector and then I'll transform it to this 64 dimensions. So h1 here would be 64 and x would be 1. So only one dimension, and from the one dimension you go to 64. So wx plus b, and then I'm passing it through a nonlinear activation called ReLU, as you saw the definition at the top, which is simply max of the current value comma 0. So it will reject all the negative quantities and pass through all the positive as it is. And then again after that in h2 I'm transforming this 64 to 128, and then again passing it through the ReLU, and then finally I am again passing it through a linear transformation to get just two quantities. So from 128 to 2. That is because in the circle we have 2 points at x and y. So now one question to the audience: why didn't I add any activation after this? So can anybody think about this? So because in the example here, right, I talked that you can pass the final output also through an activation, but here I'm not doing that. Can anybody think why did I do this?
So your x and y can be negative, so ReLU won't work, and I think same point because you'll be in 0 to 1.
Yeah, correct. So according to your data, you have to know how to write these operators. You can't simply randomly choose some nonlinear activation and expect like neural network to learn it. So you have to have some understanding of your data. You can't blindly use these libraries. So okay, so that's that. Then this forward call is simply calling this list of operators that are defined in nn.sequential. Okay, any doubts still here? Okay. So now how do we find a good theta, that is the parameters of this network, that the weights and biases, Ws and Bs. So typically we solve this following optimization problem where we want to find the minimum theta such that this loss function is minimized or sometimes maximized. So in RL we generally maximize it, but generally in machine learning you try to find the minimum. And L here simply measures the discrepancy between the predicted outputs and the true quantities. So in our case, it's simply the correct XY pairs for that particular angle. So in our case, we'll use this following squared loss. So basically error squared. So you take the error, whatever you have predicted, and then square it up, and then sum it all over all the data that you are passing through the network. So I won't go into the depth of these optimizers that are used to optimize these functions, like different classes of L. For that, you can refer to the links that I have given at the top. So currently, for now, just make sure that we'll be using this something called as ADAM, adaptive moment estimation, and explaining that would be out of the scope for this workshop. So we can simply define your loss function and your optimizer something like this. So criterion is nn.msc loss and optimizer is Adam. You pass the model parameters, the weights and biases to this optimizer, and the learning rate. Learning rate simply means how fast do you want to converge to your local minimas. Okay, so now we'll run this cell and yeah, now we'll start the training loop. So typically your whenever in the now like in today's workshop as well as in the future, if you work with PyTorch, your training loop will look something like this. You will first have to initialize something called as model.train to enable calculation of the computation graph that calculates the gradients. So like what is the gradient, so for with respect to these model parameters to update the current parameters according to that loss. So you have to initialize that using train, and then you calculate the output. So you pass in the angles tensor. So I have a batch of different angles that I have that I've randomly sampled from the data set, and then I predict the output using the model. So some predicted output, and then I simply calculate the loss here using the criteria that I defined earlier. So and versus the correct coordinates. So these are like correct xy coordinates in the data set. Then I do something called a zero grad, which is required to sort of clear the computation graph and start calculating the gradients. And loss dot backward will basically do that, like gradient with respect to all the these parameters that are there in the model. This loss dot backward will do that, and then optimizer step will simply update those parameters. And you will run this for like a few epochs. So and then in here I've added some inference code. This is required to sort of not mess with the training code here. So you can run this. It will take like max to max 1 minute. So yeah, you can see that earlier our model was predicting some garbage values, right? So at around epoch 10, so initial iterations, and the loss was also quite high, like 0.3. And then slowly you can see that the model is learning to find the patterns in the data and try to see that okay, whatever points that I'm seeing in the data set are actually a circle, and accordingly the optimizer, that Adam algorithm, is fitting to it. So you can see by epoch around 800 you have something like this. So any doubts still here? Okay. So and then you can simply evaluate the performance. So the final code. You can see that initially our model was doing very bad, and then finally it learned to predict something. So this much of a knowledge is enough for you to understand the next session, which is on BQN. So any doubts?
Will you just repeat what were the inputs and the outputs again?
Oh yeah, so input is simply the angle between 0 to minus pi to pi or 0 to 2 pi, and what should be the xy coordinate for that angle. So basically according to the circles equation it will be r cos theta sin theta, right? So predict that xy coordinate, and that xy coordinate has some noise, so you're simply making the model fit to this equation of circle. That's just a simple example.
So training data had what? Just x and y coordinates?
Yeah, x and y coordinates. So if you see the top, when I generated the data, I am simply randomly sampling angles from 0 to 2 pi, and then calculating the equation of the xy coordinates according to the equation of the circle and adding that to the data set. So this is the problem. Given an angle, you have to find x and y coordinates.
Hi. We
we can play around with the size of bits and bytes.
Yeah. I was going to come to that. So as an exercise, you can change these numbers yourself and run this code again. You would get a different result. So I'll show you. So what I'll do is I'll add tanh here and change the network sizes. You can add your own numbers, that's fine. And what I'll do is I'll make the network very small. So basically, so that it struggles to learn the equation of circle. So I'll add maybe 2 here and 2 again here and then 4. 4. So yeah, if you run this whole thing again, you might see that the neural network struggle to fit. I think it almost did learn. Okay, it did a little bad compared to the previous numbers. So you can see it was not able to fit around this region. Maybe if we train it more, might fit here. But yeah, so you can play around with these numbers and try to like sort of get a gist of how things are working.
So my question was basically by choosing different dimensions of bits and bytes, we can have different nodes in hidden layers.
Correct.
I was interested in knowing how it helps. If I increase it so large, will it going to be very helpful? Like you reduced it,
Yes.
now the performance is not that good.
Yes.
So suppose if I take significantly very high, it will always help me, or there is any optimal way to choose what should be the dimension of
So
and bytes?
there is a trade-off. So if you have too many parameters, the function approximator simply overfits. Basically, it will perfectly predict the like xy coordinates in this case given an angle. So it will not generalize that well. So I have added noise here, right? So if I reduce the noise and train it for like with very high number of parameters, it will overfit. So it will like, sort of rote learn the training data set, and you don't want that, because during inference, that is outside of your training environment, your network should be able to find these patterns in the data. And if you are just trying to overfit to that training data set, it may not generalize that well and perform poorly on something that it has not seen. So you have to generally people do a hyperparameter sweep search, there are different techniques, or maybe there is something called as meta learning. You can go into that, like finding the good hyperparameters. So solving another optimization for finding those hyperparameters. So different approaches are there. So there is always a trade-off.
Does it impact the performance of optimizers also? Because that function which is being minimized by, I think you used Adams.
Yes.
Its performance is going to down, or
no? Optimizer is those optimizers are generic optimization approaches. They don't care about how it's a generic mathematical formulation that you use to.
My question was, when you are taking too many parameters, does it impact their performance also?
It could. So that is why there are different optimizers. So depending on the use case or number of parameters or the structure of the data set, you might prefer some other optimization algorithm.
Thank you.
So the Adam is only first order, basically only working with the gradients. You might have an application where you want to work with second order information as well, that is the second derivative, but those are computationally expensive generally. So all those things are there. Any other questions? Okay, so we can move on to the different session. I hope you've been motivated enough to why we need function approximators. So you can go here and on that events page and open this DQN link. So again, as before, create a copy so that the session is a bit interactive. Go to the top. So before starting DQ1, I'll just give you a rough picture of, it's slightly outdated, but rough picture of different RL algorithms that are there. So today we'll be covering Q learning and some policy optimization approaches. So now I'll be covering DQ1, and in the next session you'll have policy gradient and actor-critic. And yeah, so you can sort of classify these algorithms according to different approaches that you are taking. So model based, model free, and all those things. So yeah, you run this first cell here, importing all the libraries, and this cell is for some plotting stuff. Okay, so DQN is like a slightly old paper, 2013, and it was somewhat of a very famous paper that blew up RL, use of RL. So like using these function approximators, and some highlights. So I'll give some highlights of why you want to use DQN. So like as Vamshi has covered in the previous session, that for continuous spaces it's infeasible to represent all possible states explicitly in a Q table. So like discretizing leads to like exponential growth in memory requirements, etc., and inefficiency in learning due to the sparse coverage. So hence this paper aimed to have function approximators to tackle this. Another issue is that it was like found that when you are doing Q learning, as you are collecting data, since there is some correlation between the data that you have collected while running the agent, the samples are not independent, sort of. They're slightly related to each other. They're not perfectly IID. And that causes instability in the training, and calculating the gradients might cause them to have some bias, which you don't want. So that is why this paper suggested to use something called as a replay buffer, which is simply collecting this data that you are running in an episode and storing it in some like some array, and then randomly try to shuffle the data and sample these state actions, next state, reward tuples. And lastly, they also found that when you calculate the target Q value in that Bellman backup, if you use the current Q table, so in this case function approximator, Q function itself, it causes some instability, like the algorithm will oscillate a lot and might collapse as well. So one small hack that this DQN paper introduced is to use another network that will be updated less frequently, and the weights of that network are simply nothing but copy of the Q network that you are optimizing using that Bellman backup. So I'll explain in the code what I mean by this if you are confused. So roughly the algorithm is something like this. You start with some initial sequence, and so this pre-processing here is involved because in the DQN paper they were working with the images, that is the image frames. So rather than the XY coordinates or X and theta coordinates of the Cartpole, they're working with the image frame of that Cartpole, so that environment, RGB image, and that requires some pre-processing for enabling some efficient learning. So basically, like making it grayscale, resizing the image, or doing some augmentation, stacking the frames, etc. So all that pre-processing is represented by this phi, and then you in the episode you collect using your epsilon greedy strategy the data. You select that action and collect the data in the environment. You store this transition phi t, at, rt, phi t plus 1 in the data set, the replay buffer, and then while training you randomly sample some mini batch of these tuples to sort of break this correlation between the when you had collected the data, and do your this Q learning update. So here this Q here is a separate network that is introduced to avoid the problem of oscillations that you can see when we run the code. So yeah, like how I showed you in the previous session, you can write the Q network function approximator something like this. instead of sequential, I just wrote it separately here. Like I have FC1 linear state, FC2, FC3, and then here at the bottom I'm doing torch.relu, passing through the state through FC1 and then to FC2, and then finally just simply a linear transformation in the end. And then a class for replay buffer, basically the data set, a simple utility tool that we are using to randomly sample experiences. And then the DQ and agent class. So here I'm passing some hyperparameters for the algorithm. So some of them you might already know, like gamma, the discount factor, epsilon. So here I think if you remember, Vamshi had somebody had asked this question: what should be a good exploration strategy? So he said that you might explore the state space early using some high epsilon value, and then slowly decrease it as the training progresses. So here we are doing something like this. We start with some epsilon value of 1, like only taking a random action, and then slowly decaying that value using this decay factor to this minimum value of 0.01. Basically 10% of the time you randomly choose an action. And then a learning rate, and I have something called as update frequency and update frequency Q. I'll show that in the code soon. So yeah, you define all the networks like the Q network, Q function, and the target Q function that you'll use for that target Bellman backup, and then you simply copy the same parameters initially, keep both the networks same, and then you define your optimizer and the replay buffer. And here you can see the select action strategy, the epsilon greedy stuff. So if epsilon is less than this 0 between this np.rand, so you randomly select it. Else you pass it through the Q network and select the maximum action, the action which represents the maximum Q value. And now to the training function. So here I have two variables here. One is t step, which is how often do I want to call the update of the Q, this Q network, like this Adam step for the Q, optimizing this Q function. And then I have one more T for Q update, basically the target network. How frequently do I want to update that network, like copy the weights of that. So if this T is modulus 0, so basically I'm at that time instance where I want to update. I'll sample the experiences. If the memory buffer is too small, then the batch size, I skip the training part, because I want some like good amount of data in the buffer. It should not happen that I'm starting with a very poor warm start. So yeah, this statement is for that. So I collect experiences, randomly sample them, and then I calculate the current Q values by passing the state, and I calculate this target, which is simply that standard equation. So reward plus discount times the maximum for the Q target here. So if you use a Q network here, you can do this as an exercise. Add Q network here, and make sure that you do it without the calculating the gradients, otherwise it might break the algorithm. So this step has to be without the gradient. So with toss.nograd, calculate this target Q values, and you then calculate the loss, so current Q value versus the target, and then you do your standard that PyTorch optimization stuff that I discussed earlier. Zero grad, backward step, and then there is one more counter for checking whether I want to update the target Q network, basically copy the weights. So I call this, whenever that is satisfied, I call this function which simply copies the current Q function weights to the target ones, and that's it. So this is roughly the training part, and this is simply some helper stuff for making it easier for us to work with the data that we have collected. So you can run this cell, define all the functions and classes, and then here is the training. So this is the function where you will run the agent and collect the data. So we'll run this for the Cartpole. For default values, I'm running it with some 500 episodes, batch size of 32, and gamma is 0.1 995 and update frequency as 2. So basically how frequently I want to update the queue network, and then the default value for this target network is 2. So you can say 1 is to 2. So that will be updated 2 times less frequently than the main queue function. So I have those things defined here. I make all the environment stuff, standard things, and then I run this agent in the environment. Here you can see with the I collect the data, I add it to the replay buffer, and then I call the train step, and then I keep repeating it again and again. So you can run this cell. So if I run it with this default parameters, you can see you'll get some plot like this. Since I have not set the seed here, basically if you're familiar with random number generation, you have to define something called a seed to get reproducible results. I haven't done that here, so you might get a different graph. And so if you want some reproducibility, you can set all those quantities. So you might get something like this, and at the bottom, so yeah, you will get some information that it took like 3 minutes or something to train for 500 episodes. And then you can play the agent here. So you can see it has sort of learned to balance the pool.
What's the what's the training data here? We have state action reward next state,
Hmm.
and the label would be what?
Label?
What's the training data like? Just the state action reward and the next state.
Yeah, so that is the standard tuple used for queue learning, right? State X. If you go to this top, state is pre-processed, like process state. In the paper, it was there. In this case, since it's Cartpole, it's a simple X and theta. So the state action are next state. When you take a step in the environment, you get some reward, right? Whenever the agent takes an action here. So execute action 80 in so simulator the Cartpole and observe a reward RT. So you take an action, you go to the next state, and you also get the reward for being in that state due to that action. So you collect this tuple and you store it in the replay buffer, this data set.
And the queue network is taking this as input, the whole tuple.
No, queue network. So queue function is simply a function of current state and action, right? So you can see. So the action that you take is trying to sort of maximize the queue value, right?
So input will be your
just the
state,
state.
and then output will be
Yeah, I think this is a good point. So when I defined the queue network here, I didn't pass action explicitly. If you noticed, I'm only passing the state, and I'm calculating the queue value for all the actions. And then accordingly, I'll select the index which represents the highest queue value, the action which represents the highest queue value.
so the network takes state as input and gives action.
Yes.
Use queue values for all state actions.
Yeah, queue values for all state.
For that state and all actions.
So it's sort of like a queue table, like if you've seen not a table, like representing the same thing. Like you give a state, you get queue values for all the actions.
Let's take it like this phi of S, no? That's
So in the paper, so I've taken this from the paper. So in the paper, they were working with images and which required some pre-processing. Since our environment is like simple Cartpole, we can simply pass that X and theta. Okay, any other doubts?
Can you go to the plot, please? X versus reward. Here I don't understand that as episodes increase, like the reward is not getting better. Sometimes it's 500, it's close to 500, and sometimes it's dropping. But you would expect that.
Yeah, it should always be there. So
No, either it should not always increase, monotonically increasing, but at least it's not like going down to zero. For example, around 200.
Yeah.
For one of the episodes, it's like 500, like where it's perfectly balancing, and next in the it's just like completely.
yeah,
gone.
so that is the problem with these algorithms. So it might be that it encounters some state where the queue values are not trained properly, since it's continuous, right? So the neural network predicted some garbage value, and then the agent did bad, and then it recovered again. So all this thing will happen. So I just took an arbitrary number of 500. You can run it for 5,000, 10,000. It might happen that it just stabilizes after a point. So this is not the final like trained thing. I just showed you as a till 500 you can get this kind of a performance.
So how do you find this then if this kind of jittering happens? How do you find that okay this is optimal policy?
So you would get some sort of stability as you keep running the algorithm. If it happens that it's oscillating continuously, then that means something is either there is some code bug, one thing, or the algorithm that you implemented is like has some fundamental flaw, or could be that it still hasn't converged, or maybe bad hyperparameter, something like that.
Hello. So the target queue network only gets updates from the queue network toward that frequency. So there's no gradient.
No. Simply copy the weights that you have trained to this target queue.
So and it's called target queue because it's trying to approximate the queue value for the next state. Is that correct?
Yes.
Thank you. Are there approaches where people have tried to approximate this whole the max over a prime in the algorithm of q of 5j plus 1, the whole thing as a network itself?
1 second.
Is that a valid approach, do you think?
This thing?
Yeah, the whole max part of it as a network separately.
I'm not aware of any such method. Maybe there is.
Okay. Thank you.
But it might happen that if you add it in the network itself, you'll always pick some greedy action, right? If you add max inside that. So, but yeah, you can have epsilon greedy outside that. So, okay, that is possible. I'll have to think about this question. Any other questions?
Yeah, so the reason we use double DQN is because you have instability of the QN, that's why you're copying, right? Like
double DQN is different. This is just DQN.
Okay, but you are using a different target and updating it because of the instability, because if you update every theta. So a lot of literature says that if you use a deeper network, then a small change in theta would not affect all the Q states, but maybe only local to the state that you're visiting right now. So in practical applications now in 2025, do people use deeper networks, or you still use the double approach only?
People have moved on from DQN as far as I know. There are better algorithms now. DQN has its own issues. So in the next session, some of them will be highlighted by Lakshmi. Some guy has the doubt in the back. Okay, so this point, I guess, right? Yes. So, generally these algorithms make an assumption that the data that you have collected, the training data in the updating has to be IID, and that is violated here because you're collecting these the state actions and the state tuples sequentially, right? So there is some correlation. And what happens is the gradient that when you calculate, when you do this, when you fit this Q value, this loss, fitting the Q function to this target value Y, the data will be biased towards the experience that you have collected, the gradients and all. So it might lead to poor generalization. So it might happen that it finds some trends in that when it collected the data, like it is always so let's say it was always falling, and it sees that it has to recover by pushing to the left, and all the data they have collected is always towards that in a sequence. And so when you train it, when you update the Q value, it will be biased to that experience only, like only pushing it to the left. But it might happen that you also want to push it to the right. That is also possible. But since you are training it sequentially, like updating the Q network, according to the data they have collected. So this bias will be induced. So you want to avoid that. So this is what they have found. So you can simply collect the experience, shuffle the data, and then using that IID assumption, you can then go ahead. Is it clear? Any other doubts? Okay, so the last thing you can just see you can run, or just for now just see these different hyperparameters that I've tried. I increased the update frequency to 6, so basically delayed queue updates, and you can see I'm not updating it as frequently, and so there is some oscillation, and it doesn't look like it has stabilized yet. So you can see compared to this plot versus this plot, there are more oscillations. So all these things you will notice when you play around with these hyperparameters, and so it's good to understand why that is happening. So you can look into literature and try to, there's some mathematical flaw in the algorithm itself, so you can look into approaches that tackle this. So all these things you have to, according to your problem, you have to identify that. So but it still does well in the final result. But yeah, you can see there are some oscillations. Might happen that in the other environment it didn't do so well. So all these things are always there. And here in this cell I am updating it every time, and you can see it climbed up early very well, but there are still more oscillations compared to this graph. So here it climbed up a little late, but there are a few oscillations compared to this one. And it might also be that this is due to the seed. So that is also, so you have to run this across generally like a good bunch of seeds, like 20, 30, to get a rough idea about what's happening. And then you can see here the agent didn't do so well. So it's like the pole is falling and the reward is also less. And in the final one, I decreased the gamma value, and approximately about, like, it looks like it did well in the initial period, but then there was a lot of oscillation, but still it at least learns. So unlike this case, so all these things are there, and in the next session you'll know some of the drawbacks of BQN and how you can tackle them. So I guess that's it. Any other doubts? You have a doubt? Okay, sorry. Okay, so we can start the next session. You can go to the events website and open these two links.
This also can click more trend. Like this.
Yeah, good afternoon everyone. I'm Lakshmi Mandal, a PhD student in the Department of Computer Science and Automation. I'm working with Professor Sallabh Bhatnagar. Yeah, so already you know about DQN. So that is a value-based reinforcement learning algorithm. So do you think is there any limitations in the DQN? Yeah, okay. There are some limitations in the DQN. The goal of the DQN is to optimize the Q function, and that Q function used to infer the optimal policy. And DQN makes use of the projected Bellman operator that does not guarantee to get the optimal policy. So here Peterson and others claimed in their paper, the empirical design in reinforcement learning in 2023, that they observed catastrophic failure events for DQN across nearly every tested domain, such as lunar lander or Creep world. So here I have just run the DQN code in the lunar lander environment. So later I'll go in depth of lunar lander environment. Just now I want to show the results, that how I'm getting the results in using DQN in the lunar lander. So I can see that most of the time the agent is getting high negative reward. So that means the agent is failed to learn using DQN. And let's say if I play the video, yeah, it's getting crashed, so it's not learning well. Okay, so what is the alternatives of DQN? Okay, so the alternatives are the policy gradient algorithms. The policy gradient algorithms directly optimizes policy parameters in the policy space. So the first policy algorithm I'll talk about, the Monte Carlo policy gradient algorithm. First I'll go the overview of this algorithm and I'll explain the code later. So this algorithm is taken from the Reinforcement Learning and Introduction by Sutton and Bartow book. In this algorithm, we take a differentiable policy parameterization pi as an input. And here the algorithm parameter is the step size alpha. This step size also we call the learning rate. At first, we initialize the policy parameter theta to 0 factors. And then for every episode, we generate the episode following the parameterized policy pi. Here at time t equals to 0, the state is S0, the action is A0 and reward receives is R1 and so on. So we can see that for every time step within the episode we are getting this pair, the state, action and reward. So in every episode for time t equals to 0 until the end of the episode, we calculate the discounted return and we denote it by using G, or at time t we can call it as GT. So GT is the sum of discounted rewards, discounted single step rewards. So this is RK, is the single step reward at time K. And then we use this discounted return to update the policy parameter theta. Here we can see in this line that we are using this learning rate alpha, the discount factor to the power t, and then this discounted return and the gradient of the log of this parameterized policy pi. In our code, we have used softmax policy parameterization. So this is the formulation of softmax policy parameterization. So the policy pi for state A given for a action A given the state S and policy parameter theta, that is the e to the power theta transpose phi of S comma A divided by sum of e to the power theta transpose phi of S comma A dot over all actions A. So what is here this phi of S comma A? So this is the feature of this pair, state and action pair. In our code, the neural network extract this feature. Now I'll talk about the lunar lander environment. So the lunar lander environment is a classic rocket trajectory optimization problem. So if we want to apply, if we want to solve this problem in the RL framework, we need to know what is the state space, what is the action space, and how is the reward formulation. Yeah, if you want to know in depth of Lunar Lander, you can go to their original website, this, and yeah, you can check the details. Yeah, you can just search Lunar Lander gym, so you'll get it. So in this here in the Lunar Lander, the state is a 8-dimensional vector, and here we have 4 actions. So do nothing, fire left orientation engine, fire main engine, and fire right orientation engine. So yeah, this is the action space, and the reward formulation is like this, that if the agent move from the top of the screen to the landing pad and coming to the rest, it gets 100 points to 140 points. If the lander crashes, then it gets -100. If it comes to the rest, then gets +100, and so on. Yeah, you can just check it. To run the RL algorithm in the Lunar Lander environment, we need to install Gymnasium Box 2D. So yeah, I have just used the pip command to install it. In this, yeah, where you will go to this link, and then, okay, I'll get this only. Okay, yeah, you can just install it. It will take some time. I have already installed it, and then we need to import basic torch libraries, required torch libraries. So I have just imported it. So as already Aditya talked about, that torch.nn is for neural network, torch.optim for optimization purposes, and so on. Now this block of code I have used to display our live plot and the video. So I am not going to it, because this is not basically part of our original algorithm. Just you can check it. Yeah, now I am coming to the main part of our code. First, we need to define the policy network. So at first I define the policy network here. Here we have 3 layers, 3 neural network layers, and we need to pass the state size and action size here. So in the first layer, we have the number of neurons equal to the state size, because we will take the state as an input. And then in the hidden layer, I have just specified the number of neurons equals to 256. So you can try with a different number of neurons. And in the output layer, the number of neurons equals to the action size, because in the output I will get the distribution of actions. And the one important thing here to be noted, that in the output layer we need to use the softmax function, because we are using the softmax policy parameterization. So from this output layer, I will get the distribution of our actions. And in the above, in the first and second layer, I have used the ReLU activation function. Now if we want to optimize any parameter in the neural network, we need to know the loss functions. So here are some different loss functions: the mean squared error loss, binary cross entropy, categorical cross entropy. So when we use the mean squared error loss, so if the target value is continuous, let's say for the regression problem, we know in the machine learning, then we use the MAC error. For the 2-class classification, we use the binary cross entropy, and for the multi-class classification, we use categorical cross entropy. Yeah, this RL problem is not a supervised learning, but we can see that let's say we have m number of actions and we want to select the best possible action. So that means we want to label a data to its best feasible tag. Then yeah, we use that categorical cross entropy. So in this code also, yeah, I have used the categorical cross entropy to optimize the policy parameter theta. Now I am defining the policy agent. Yeah, okay, yeah, here you can see it. So in this policy gradient agent, I pass the state size, action size and the learning rate. Here I have specified 0.001 and discount factor is gamma is 0.99. You can try with different values of learning rate and discount factor. So then I am just instantiating the policy network that already I have defined in the above. And I am using the Adam optimizer. Already Aditya talked about this Adam optimizer. This Adam optimizer helps us to adaptively learn the agent. And then I am coming to the select action function. So this function helps us to take a state and then provide the action. So in this case, first I am converting this state to a state transfer and then I am getting the policy from the policy network and then sampling a action from the policy, current policy, and then calculating the log probability of the current action. This log probability I will be using to calculate the loss. And then I am coming to the update policy. So at first actually I am explaining all the blocks and then I will explain the main learning part. So in the update policy, at first I am calculating the discounted return that in the algorithm that is denoted by G. So that I am calculating first and then I am normalizing it to get the better learning by subtracting its means and dividing by the standard deviation. Sorry?
What's the action space?
4. Action space. Yeah, for the lunar lander that already I have discussed that the action space is this. Okay, yeah, that this is do nothing, fire, sorry. Yeah, do nothing, fire left orientation engine, fire main engine and fire right orientation. So here 4 actions are available in this lunar lander environment. Okay, then for every log probability and discounted return pair, I am calculating the loss. This loss is equals to minus log probability of the current action into the discounted return. So why I am here using this negative symbol? Because this PyTorch framework by default calculate the gradient descent, but in this case our algorithm is a gradient ascent algorithm because this is theta equals to theta plus this. So I am performing the gradient ascent. That's why I am putting this negative symbol here. Okay, and then I am keeping just track of this policy loss so that I can use it to optimize our policy parameter. And then 3 lines are very important to learn the to train the policy parameter. So at first I am resetting the gradients to 0 by using this line, the optimizer dot 0 grad, and then this line, this policy loss dot backward, this is computing the gradient of the policy loss with respect to the parameter theta, and then in this line we are just updating the parameter theta. So okay, this is about this block, and yeah, this block is, this function is just calculating the discounted return G. And now this learn policy gradient, in the learn policy gradient I am passing the environment. So you can pass the Cartpole or like some other environment also for what you want to use it. And here I am specifying the number of episodes equals to 800. You can try with different number. And I am calling the policy gradient agent here. And then now for every episode, at first I am resetting the state and then within the episode, that while true, that means while I am within that episode, I am sampling action and from the current policy, and then I am observing the next state, the single step reward, and the policy is already terminated or not. This done, yeah, will give us true or false. If done equals to true, that means that policy, the episode already terminated. And then I am keeping track of this single step rewards, and here I am calculating the episodic reward so that I can use it for the plotting purposes. And after end of this while loop, that means after end of the episode, I am updating the policy. Updating the policy, that means I am updating the value of the theta. So here key point is this, that we can update the policy parameter theta after end of the every episode. And this is just for plotting purposes. Now if we run this code, the learn policy gradient, that is learn PG, so we can see this kind of plots. Yeah, I can just train it. This lunar lander is a bit complex environment, so it takes some more time. Okay.
Do we need to consider terminal state to be called an episode, or even the intermediate state we can take? Like we have a capital of 800, no? If we have not reached a terminal state, still we can use that trajectory for updating the policy, or we necessarily have to reach a absorbing or a terminal state to update the policy?
Yeah, in the policy gradient, in the Monte Carlo policy gradient algorithm, we need to reach to the termination state or the goal state. After that only we can update, we can perform the update of the policy parameter. Or let's say if if this lunar lander perfectly lands it on the moon surface, or it get crashed, then this episode will get terminated, and then only we can perform the parameter update. Within the episode we can't update the parameter update in the Monte Carlo policy gradient algorithm.
The definition of an episode is that we need to have necessarily a terminal and absorbing state.
Yes, because these what I am discussing now, this is for the episodic case. I think Bamsi in the first, he already talked about the finite horizon and infinite horizon reinforcement learning algorithms. So in the infinite horizon reinforcement learning algorithms also, we have the episodic case as well as continuous case. Then if that game is continuous, then there is no termination at all, but for the episodic case we have a goal state. So yeah, if the agent reached to the goal state, or if abruptly terminated after some time, that means after the end of the episode only we can update the policy here. Yeah, so do you think, is there any limitation in this algorithm? Anyone? I think what he asked, this is related to this only. Okay, so yeah, I can say it. So the limitation of this Monte Carlo policy gradient algorithm is that we can update the policy after the end of the episode. So we need to wait till the end of the episode. So that's a bigger drawback. Yeah, in the scenarios when we don't know when the episode will end, then the trajectory length is unpredictable, and our theta update is also unpredictable. So that's the demerits of this Monte Carlo policy gradient algorithm. Okay, if you run this code and do this plotting, so you can get the episodic reward for each episode, and the plot will look like this. So I have run this code here. I don't know how much it runs. Okay, yeah. So as I did not specify the random set, now this is looking something different. You can try with different values of learning rate or I mean different values of episodes. You can do it better. So previously when I run this, yeah, I got this plot, and if I play the video, yeah, lunar lander is able to land in the moon surface. So yeah, this is how it should behave. Yeah, you can try with different hyperparameters and check how it is learning. Any questions regarding? Okay.
So when I try to run this, I'm getting this average reward, the one that you get at the end. It's a negative number, but I don't see any decrement operation in the code per se. So how could we get a negative number?
Okay. As I already discussed about the reward structure of the lunar lander, so we can see that if the lander crashes, then the agent will get -100, or if it fires to its main engine, from its main engine, then it will get -0.3 for each frame, or if it's fired from its side engine, it will get -0.03 for each frame. So that's why you are getting these negative rewards. You can try with, like, for more number of episodes or different values of hyperparameter, yeah, you will be able to get the good reward.
Hello. I in the morning we had a session where sir said that for some thetas we need to have a condition that theta is giving you some stationary Markov chain and stuff like that. Is that assumed here, or are there formal ways of ensuring something like that, or is that completely different from what's going on?
Yes, like as this also I mean follows the Markov property. The Monte Carlo policy gradient algorithms also follows the Markov property.
But we had a condition in the model. Again, I might be mixing few things here. But that the idea that when you parameterize a policy by some theta, for different values of theta, we need to ensure that the appropriate a theta that we get, the transition matrix that we get, has a stationary distribution also with it. But we were not sure whether it's possible to do that, or is that assumed generally, or
Yeah, when we prove, when we come to the proof like theoretical convergence, we assume that okay, like the theta, you want to say that the policy parameter theta is what is that?
So because each theta gives a policy finally.
Yes.
So that policy induces a state transition matrix, and that state transition matrix should have a stationary distribution.
Yes.
Right.
That's the flow. Yes.
So then each theta should be able to do that.
Yes.
How do we ensure that here? Do we ensure that here?
We ensure this here also. Like for our theoretical proofs, we ensure this. The policy gradient algorithm follows that, the stationary distribution. So actually, I'm not going to the the theoretical background, but yeah, that we can ensure by policy gradient. Let's say for the Monte Carlo policy gradient algorithm or actor-critic. So one thing we can do, that we can project this theta within a space, policy space, and we can ensure that.
Why is DQN not able to do that?
Actually, DQN is not optimizing the policy parameter directly. The DQN is optimizing the Q value function using the projected Bellman equation. Okay, but here we are optimizing the policy parameter theta directly in the policy space. So that's why I mean we'll get the optimal policy by using these policy gradient algorithms. So you can you can check that, yeah. But yeah, I mean already you have seen na, that there are we were performing the max of max of q values. Okay, like we want to select the action which is maximizing the q value, right? But here you can see that we are directly optimizing the value of theta. Any other questions? Okay, as we already know that the disadvantage here is that we are updating the policy after the end of the episode. That means we are performing the update after this while loop. So how can we remove this disadvantage? So what are the alternatives? So one thing we can do, that we can put this policy update within this loop, right, within the while loop. Then we can update the policy within the episode. So that's how actor-critic algorithm comes. So now I'll talk about the one-step actor-critic algorithm, and this is also for episodic case what I am talking, and this also taken from the RL and Introduction by Sutton and Bartow book. Yeah, in the actor-critic algorithm, as the name suggests, here we have two networks, actor and critic. And the actor-critic algorithm takes the advantages of both value-based RL algorithm, what Bamsi and Aditya talked about, and the policy-based algorithm, what I just talked about. And how it is happening here? Because actor is optimizing the policy parameter and critic calculates the value taking that policy and optimizes the value function parameter. So that's how actor-critic algorithm getting the advantages of both. In this case, we have two inputs, a differentiable policy parameterization pi and a differentiable state value function parameterization v hat s comma w. Here w is the value function parameter, and already we know that theta is the policy parameter. As we have two networks here or two recursions here, so we have two step sizes, alpha theta and alpha w. So alpha theta is used to update the theta, and alpha w is getting used to update the value function parameter w. At first we initialize the parameter theta and w to 0 factors, and then in every episode we initialize the state s, and then until the termination of that episode we sample action A from the current policy, and then taking action A we observe the next state and single step reward. Then here we calculate the TT0 error. This delta we can say about that this is TT0 error or advantage function. So this is the difference between the target value of the current state minus the current value of the current state. So the target value of the current state is single step reward plus discounted value of the next state, and we use this TT0 error to update W as well as theta. In the W update we are using the gradient of the value of the current state, and in the update of theta we are using the gradient of log of parameterized policy pi, and then we set the next state to a current state. So this is the brief description about the actor-critic algorithm. Now I will go to the code. Yeah, this block again used for displaying the plot and video. Now as I discussed that we have two learning rates, one is for actor and one is for critic. So I just specified this and this value. You can try with different values as well. Mostly in our literature it is said that the learning rate of the critic is greater than the learning rate of the actor. Yeah, you can check that. And here I have specified the discount factor gamma is 0.99 and number of episodes to 100. You can try with different values of this. Now we have two networks. The structure of the actor network is similar to the policy gradient network, as actor will provide us the uh, uh, distribution of the actions, and the critic calculates the value function. So we can see in the last layer of critic, this is linear, because here in the last layer of critic there is only one neuron, because if we give a state as input, we will get the value of that state. So that's why the outer layer of the critic is linear and number of neuron is just one. Now I am coming to the main training loop. Here again I have taken this lunar lander environment and I have instantiated the actor and critic, and again I am using the Adam optimizer for actor and critic both. Now for every episode I am resetting the state, and then within that episode we can see that within that episode I am updating the actor and updating the critic parameter as well. So within this episode, at first I am getting the policy. So I am getting the policy by providing the state to the actor. So actor is giving the policy, and then I am sampling the action from the that policy, and then observing the next state and single step reward, and if the episode done or not by using the action. Now here it is to be noted that I am getting the value of the current state from the critic, and getting the value of the next state also by passing the next state to the critic, and calculating this delta. I mean that delta here. Yeah, this is the advantage function delta. Yeah, this is reward plus gamma into next state value minus current state value, and I am using this delta to update the actor parameter as well as critic parameter. So why I am performing that dot detach here? Because here I want to calculate the gradient with respect to the theta for the actor parameter update, not with respect to the W. So that's why I am detaching the computational graph from the advantage function, and again I am putting minus symbol here so that I can perform the gradient ascent, and then updating the actor. Now I am updating the critic. So one main difference to update in the actor and critic is that in the update of the actor I am computing the categorical cross entropy in this line, but in the update of critic I am computing the mean squared error, because yeah, you can see that I am squaring the advantage function and I am using it as critic loss, because we want to optimize the value function here, and that is a continuous in nature. But for the actor I want to select the best possible action from m number of actions. Here for the lunar lander we have 4 actions, so we want to select the best action. And yeah, this is the end of the training loop, and this piece of code is written to collect the state, next state reward, and done to play the video. Yeah, if you run this algorithm, we will get this type of plot. So this plot is about the episodic reward with respect to the number of episodes, and we can see that in the DQN we are getting high negative rewards for the lunar lander, but here we are getting the positive rewards after certain episodes. Now if I run the video, yeah, it is able to land it in the moon surface. Okay. Yeah. So so is there any questions regarding this?
So you said actor-critic, there are two networks, right? So can I consider GAN also as an actor-critic? Generator and discriminator, we have two networks, and like one network is kind of trying to, generator is trying to learn a distribution, and discriminator is giving it the direction to learn it. Right? So if I see it in that way, can I see GAN as an example of actor-critic network?
Actually, in GAN, like that, two networks are incompetitive in nature. Okay, but in actor-critic, they are interacting each other so that the policy can be in the better and better. So in the GAN, you can see that the one network is generating some data, and other networks says that it is false or true. I mean, it's discriminates. Okay, but here it is just giving the value function regarding that policy, so that it could help the actor. So it's kind of collaborative in nature.
Thank you.
Yeah, back.
So, how do you ensure the convergence of reinforcement learning using this actor-critic network?
Okay, like in coding purposes you are asking, right? Yes, yes. So one thing you can do, that we have this network structure. Yeah, actor and critic, we have two network structures. So based on your environment, you can just modify your network structure so that that captures the feature of that environment well. And another thing is to that you can tune the learning rate. That learning rate here I have specified in the actor critic 0.001, and yeah, here 0.0001 and 0.0005. So you can tune it, and then another thing, you can tune the discount factor gamma. So you can just specify 0.95 or some other values, and I mean, we need to tune it, and we need to try for more number of episodes so that it gets the convergence. Here I have just run it for 1000 episodes or 100 episodes, so you can try with more number of episodes and check it. And another thing that Aditya tells, that we can try with different random seeds. So let's say you can try with 20 random seeds, and you can just average it out the total reward, and you can check that how is the average rewards. So in that way, yeah, your agent can learn in a better way.
Thank you.
That's it.
In DQN, you said there is an instability problem. That because using the neural network, we are trying to get the loss where the ground truth is not known, but it is estimated using a Bellman equation. Is that the reason why there is instability? Because we don't have the actual value, but we are using only an estimate.
Yeah, so I mean, I said that DQN does not guarantee to provide the optimal policy. I mean, selecting the best possible action, because it is learning the Q value. it is not directly learning the theta, policy parameter theta. So that's the reason that that does not guarantee the optimality of the theta value, theta equals to theta star.
So, is there any solution instability, and is there a relation between actor-critic and DQN there? Like, because DQN is unstable there, we are using a similar network based approach here, a neural network based approach here. So, do we have the same instability problem here? Is there a relation?
No, actually in Actor-critic we are using both the advantages of both the value based RL as well as the policy based RL. So you can see that in the DQN also, like in the DQN this they calculate the TD0 error, and here in the Actor-critic the critic also calculate the TD0 error. But one advantage here is that we are optimizing the policy as well, the policy parameter as well, by using the actor. Okay, and we are using that policy parameter to get the value function. So as we are simultaneously optimizing both the policy as well as value function, so that's why this can perform in a better way and achieve the optimal policy that DQ1 can't. Yeah, so just one limitations here in the Actor-critic network is that we can see the high variance in the reward. So that limitations we resolve in one of our work that is collaboratively done with Professor Raghuram Bharadwaj and Professor Saurabh Bhatnagar. So this work is variance reduced deep Actor-critic with an optimally subsample actor recursion. In this we just delayed actor update, and we are updating critic in every step, and this is published in IEEE transaction on artificial intelligence. If you are interested you can check it. Yeah, thank you.
Okay, so before you guys leave for the break, we just want to let you know that we have a robot demonstration here where we'll be showing you how you can, not these algorithms exactly, but some of the work that we have been doing based on top of this to deploy on the real world robots. So it will be like a 15-minute session, so please make sure you come back soon. And guys, you guys can leave for the break.
Thank you. Just a short
That's why the name stochastic.
That's not why it is.
That is why it is.
There's no crowding and you don't have issues in viewing the robo, in case you are interested, we request that you please occupy the first 3 rows. Okay, you may have difficulty seeing it from behind, so in case you are interested, can you repeat? Sorry, I can't hear you.
Microphone is off. He's not able to hear you. भाई इधर ही बैठो तुम, इधर ही बैठो। नहीं, सब लोग को इधर बुला रहे ताकि इधर दिखा सके। हाँ, इधर क्राउडिंग ना हो इसलिए इधर।
Can you hear me now?
इधर नहीं।
Yeah. So they are planning to have a robo demonstration so that there is no crowding. I'm requesting everyone to come in the front. Okay, and in case you are not able to see, you may want to stand up, but please don't come down on the corridor and let's not let a situation unfold where we damage the robo and also damage ourselves. Okay, so whatever it is, please try to stand up only in your place and let's see if you can learn something better.
I have the mic. Okay, so hi again. I am Aditya Shrivatkar. I am a PhD student at Robert Bosch Center for Cyber Physical Systems. I work under Professor Shishir Kothari, and this is our lab, Stochastic Robotics Lab. And today, like in this short 15 minutes demo, I'll show you something that we have been working on for quite some time. And so to talk about some of the research that spans specifically robot learning. We also work on other topics, but since given the context of this workshop's topic, I'll just talk about this. And and I'll also motivate you how you can extend whatever you've learned today, like all these algorithms, DQN, Actor-critic, policy gradient, to these real world robots to solve some real like tasks that are there. So so let's get started. So as you saw that our research focus is robot learning, not reinforcement learning. So what is that? So it's simply an interdisciplinary field of machine learning and robotics. It doesn't just include reinforcement learning, but other algorithms as well. And here the goal is to enable these systems like robots to learn new skills or adopt in dynamic environments. As an example, like of a skill would be something like you want a cloth folding robot in some factory that arranges different items, or maybe cooking robots, or transporting some goods from one place to the other in some warehouse, etc. So now coming to our lab's focus, so legate locomotion, which is one of the major topics that we focus on, and why do we need reinforcement learning or robot learning? So, well, the main benefits of if you know anything about these classical methods is that they have interpretability of the decisions that they take, and they can enforce certain constraints that you might have at the deployment stage. Like, let's say you don't want your robot to collide with the obstacle with some formal guarantee. That could be one example. Or maybe respecting some motor limits, like you don't want to wear out these actuators that are there on this robot soon enough. So that is that. So but the problem with these classical approaches is that they lack the ability to generalize to all situations. More specifically, like you want let's say in this case, the quadruped robot to not only work on this relatively flat surfaces, but also on, let's say, dense forest areas. So in such cases, these methods don't generalize that well. Further, they also make a lot of assumptions which limits their capabilities on what type of tasks they can solve. So let's say you want to solve a task of loco manipulation, where you want the robot to move something from one place to the other, as well as climb or maneuver over some complex terrains. So there, these methods face a huge bottleneck. And lastly, these methods, like classical approaches, they have some notion of the system, basically some dynamics model, which is generally a simplified version of what would happen in the real world. So it's not an actual physics model, but some simplified version of it. That also limits their capabilities. So this is where reinforcement learning for legged locomotion currently stands. So this is the state of the art, where this robot called Animal, ANYMAL, Animal can sort of do all these parkour behaviors in this really complex unstructured terrains, and this has outperformed all the classical works that have been there so far, and can even show some robust locomotion over such like challenging in such challenging environments. However, main issue is that these generally lack interpretability. Like, you don't know what the robot is thinking at all. Like you don't know what the robot. It might be that the robot will take some unsafe action, or might damage itself. You will not know that beforehand. That is there. So it generally, these methods do not provide any context as to why that decision is being taken, of, let's say, climbing over this, but maybe not, or you could have avoided it, all these things. And like I said, and basically these methods generally cannot handle constraints, so to speak. So now I'll talk about some of our work. So for RL, for legged locomotion, on how we are trying to solve this issue of interpretability and this issue of this black box nature, and sort of giving some safety guarantees and all. So while traditional techniques for walking include this model based design, we are focused on like having some reinforcement learning aspect to learn some like behaviors like let's say in this case sidestepping or trajectory steering, trajectory shifting using parameterization approaches. What do I basically mean by that is that instead of directly giving me so directly giving the robot action like to the motor, I will instead try to sort of predict parameters of a, let's say, spline or a polynomial. Using that, what can happen is I can sort of visualize what the robot is sort of going to do. Is it going to increase the width of that spline, or is it going to change the frequency of it? All these things I can sort of infer from that and try to design my this architecture better. So like as you can see in the video, so instead of if I would have ran like let's say some vanilla policy gradient algorithm or actor-critic that directly commanded these actuators, it would have been a high jittery and it would have done some random behavior to achieve that profile. But since we are sort of parameterizing it using some these functions like splines or polynomials, we can sort of get a smooth behavior and some interpretability attached to this agent's actions. So we have tested not just in simulation but also on some custom built platforms in our lab. So this was back in 2022, and we built several platforms after that. So this Stock 3, Stock Lite, and then this is the latest robot Mule. It's a big sort of industrial purpose robot. And so like our efforts still here have been like trying to provide interpretability, but still there is some lack about like it still lacks in planning, which is a major strength of some of these classical approaches. So now coming to our latest work, PIP-LOCO. So a proprioceptive infinite horizon planning framework for quadrupedal robot locomotion. So this was done like a few months back, where the key idea is to sort of incorporate these benefits of planning by that is like knowing beforehand what actions are good and according to some notion of the like task or in the system, and making sure that it's abiding to some constraints that we might have. And I won't go into the details of that because it's a bit out of scope for this session. So I'll just directly show you some of the results that we have. So like let's say you ran some vanilla actor-critic algorithm that you just learned in the previous sessions, like like a while back. Well, you can see that even like after thousands of iterations, these baseline algorithms are doing pretty bad. Like they're not outright collapsing. You can say that they're not able to learn even this simple task of walking only on these flat terrains. So yeah, this is one of our results. Then show you some of the hardware stuff that we have done. So by the way, that stair climbing is like all blind. There is no camera attached to the robot. So it simply gets some reactive feedback from interacting with the environment and then accordingly trying to adjust its footsteps and sort of trying to climb. So it is having those benefits of interpretability and planning as well. So we'll show this demo of this method here on this robot soon. So yeah, and you can see it can handle some really high drops like of 45 centimeter and all at the top right. And now our current efforts are to sort of extend this with different modalities such as vision, so that it can even perform better or maybe some loco manipulation tasks, etc. So yeah, that's it for the this short presentation, and this is our team. So yeah, we'll now proceed to the demonstration. Yeah. Which slide?
The second one, I think.
Second one, okay.
Where you have used
This one?
the planning.
Planning. This one?
Yeah.
Hmm.
So is it model based?
Yeah. So we are sort of combining MPC and RL. So MPC is this classical approach, model predictive control. I think there is one of the talks here in in the later sessions of this workshop where the professor will talk about this, how you can what are the drawbacks of MPC, what are the drawbacks of RL, and how you can combine them to achieve something like this. So that talk will have all those details. I'm just sort of giving some highlight of our lab's work.
Yeah, because the planning requires model based, but in the presence of unstructured environment, how do you handle this situation?
Yeah, so this is proprioceptive, that is no vision. So that is why this has that drawback. It will be reactive, not proactive. If we have some vision modalities and some really good dynamics model using some inductive biases, then we can have that sort of make this dynamics model predict even in that unstructured terrains. So let's say you have some point cloud surrounding. So basically some exact definition of how these chairs are arranged. I can use my dynamics model that is trained with this data to navigate around this environment.
Basically using vision based.
Yeah. That is our current efforts right now, extending this to vision.
Thank you.
That happens sometimes. Robot is a bit unpredictable. Okay. So we are not going to show all that stair climbing and all because since there are a lot of audience and might damage stuff. So just simple flat ground walking for now. Maybe you can show some high speed running, but that's possible. With just full throttle.
Sir, hello.
Okay.
Sir, ಸ್ವಲ್ಪ ಗ್ಯಾಪ್.
Does the weight and shape of the robot has influence on this?
Hello.
Yes, so if we let's say add some payload to it, this current policy is not trained to handle that. The robot will simply go down. But we can sort of in the simulation itself train it to handle all those things. And so that's some of the work Vamshi is working on, like how to make it adaptive to different system parameters.
Excuse me. So is the policy being trained directly on the hardware or?
Yeah. So training hardware is very difficult. You will most certainly damage the robot. instead what we do is train in simulation with lot of domain randomization. What I mean by that is we'll randomly change the parameters such as mass, friction, link lengths, maybe add some perturbations of for different magnitudes of forces, etc., to make it sort of robust to like all these changes, and then deploy it on the hardware, because there is always some symptorial gap. So whatever you saw right now is policy is just being robust, it's not being adaptive. So there can also be this question of wanting this thing to be adaptive to the changes. That is a different thing. You don't want it to be too conservative. If the mass changes, let's say in the real world, you drop a payload, it should be adaptive to it, not robust to it. So all those things are there, and different approaches are there to tackle this. And training on hardware, people do it, but it is generally generally they have some baseline policy that is good enough, and then they fine tune it on hardware. Directly training from scratch will most definitely damage the robot. There are people who work on flying robots.
Where is interpretability incorporated here?
In the planning. So, like there is a dynamics model which will predict what the robot is going to do in the future. Using it might not be perfect because obviously there is some gap, and then it will calculate sort of the cost of the trajectory, like how good that trajectory is, and try to adapt the actions according to. So yeah. I think battery, maybe bad connection or something. So it will adapt those actions and make it sort of safe. So you can it'll optimize online. So that is where the interpretability is. Like what the robot is thinking.
What kind of memory does it have? So when we walk on stairs, 1 centimeter gap in the last step can make us fall. So does it have that kind of memory, like prediction?
No, so its behavior is completely reactive. So if you've ever seen a blind person climb stairs, he'll hit the stairs with some stick and get a judgment of what's there in front of him. So this is the current policy that we're showing is something similar. It will hit the stairs, maybe it's 1 centimeter off. You will see that okay, maybe things are not going as expected, and then accordingly adjust to the surroundings.
Hello. So can we incorporate some kind of memory of the past events?
Yeah.
So that it knows that okay, I expect a stair of this height.
Yes. So this one was without vision, right? It is like completely blind.
But even without vision, so it's walking on the flat ground right now, and the next step it takes
it has implicitly learned to do that in training. So this reactive behavior. So if I don't think I've added a stairs. So it starts as soon as it sees that there is a stair, it will adjust its posture and then follow the same pattern of climbing. But then as soon as the stairs end, it will again sort of go back to normal, being normal. So you can see that it adjusts its posture. The legs are now lifting more on the stairs, so it can sort of get out of that situation.
The current state here means the state of the
robot,
but not the
yeah. Since it is blind.
Yeah. So only the
robot. So like orientation, then the joint angles, like what is the angle of each this link, all those things.
And it's more Markovian. It's only the current state that.
So we have done some ablations. So what people generally do is they construct a history of observations and then use that as a state, because just the current state might not be enough to infer what to do. So we have also done some ablations of what is a good history length. Like can this robot just work with history length of 1, basically the current observation, or does it need like 10, 20? So there are some works that require 50. If 50 time steps of history, then take the next action. So all these things we have done.
So Aditya, you showed one of the videos where 2 people were holding the robot to train time.
This one?
Like as if they are taking to walk or guiding the robot. I don't remember which slide, but the question.
This one?
Yeah, something like this.
This is only for safety because this is like a 70 kg robot and it can damage you, might fracture your leg or something.
So extending the question you asked on the memory, let me say this robot is employed to do surveillance for the entire IISc campus. Okay, with vision. So what kind of a memory you have to?
You mean constructing the map of the environment? Yeah. So there are algorithms and there is research on that separately. That's a complete different field on its own. Our lab doesn't focus on that. We try to focus more on this control aspects, planning aspects and all. But we'll slowly move to that.
Okay, but that's a possible use case.
Yeah. But I am not that familiar with this advancements in this mapping and all these things. Localization mapping. But yeah, I'm pretty sure there are sophisticated algorithms for that.
So this is just a running suggestion that occurred to me. So given that you are planning to extend to vision modality, so like my core research area is some explainable AI. So in vision, we do have a technique like by which you can localize which region the model is focusing on and getting the prediction. So something like that. So on this, you are showing like it is adjusting the step size, it is adjusting its orientation. So you were showing that kind of interpretation. So how it is thinking, that you can visualize. So maybe if you can add another modality that it can, as a voice output, it can say that adjusting step size or something like that. Then, so I do remember while I was going through the motivation for why explainability is needed. So there is an incident of self-driving car not detecting a pedestrian. So if that model is able to give a voice output, say that I'm detecting so and so, and if we detect that the robot is making a mistake, maybe there is a person who's controlling it, so you can immediately stop the robot. So you can maybe think of this as an additional
making it more simpler to understand. Yeah. Currently, you will need some level of expertise to understand what its thinking is. Yeah.
With vision, maybe this voice or audio output modality can also be added. That's a running suggestion.
Yes. Yeah, it's a good suggestion. Okay. One more doubt, please.
So here there are infinite possibilities for the actions also, right?
Yeah, it's a continuous action space. Yes.
So you build that with that similarly, like which kind of algorithms? One or two you can name.
So we are using PPO, proximal policy optimization, but it's not a vanilla PPO.
Okay.
We have made some modifications to the whole structure to make it suitable for this planning, interpretability, all these things. So you get a baseline like this, learning some baseline policy warm start for the planner. That is done by the PPO, but the PPO policy also takes some extra inputs regarding these, like what the robot is thinking, the dynamic stuff and all. So that is like separate addition on top of it.
Just one clarification. So you are saying that you are using splines or polynomials, so you're not using a neural network and just using a...
No, we are using neural network, but instead of parameterizing the actions directly, we try to, so let's say you have some equation A sine omega t, okay? We will make the neural network predict the amplitude and the frequency and maybe the phase also, A sine omega t plus 5.
Okay.
And then the final action will be output of whatever comes up after that computation of the like whatever this we used, parameterization method.
Okay, thank you.
Yeah, one more question. I think it's there also.
So when you say you're actually predicting the shape of the curve, how much in the future are you predicting? Because now let's say you are going to some place which you're not supposed to. the person who's controlling it needs some time to react to that, right? So how much in the future? Yeah.
So that is a hyperparameter. You can so there is something called as gate cycle, which is the time taken for all the legs to complete one walking cycle. So swing phase and stance phase, like for all the legs. So so how frequently do you want to change those parameters of the spline? It is a hyperparameter. You can change it like every time step, or maybe only 50 time steps after every 50 time steps. So depending on the how responsive you want the robot to be, you can change that parameter. There was one more question there.
Can I know what is the total cost of this robot?
Cost of?
Total cost.
So this is this one, the one we showed just now, was a ready-made one, like a company called Unitree. They make it. Due to import stuff and all, it is like around 15 lakhs, 12 to 15 lakhs. But if you look at the USD price, it's like I think $5,000.
So it is not possible for individual.
I mean, if you're rich enough.
So in the reward structure, what is the energy term?
Energy is there is something called as cost of transport, like energy taken to move from one place to another. So the energy is like this mechanical energy. So that energy, not something else, not electrical, mechanical. So tau, absolute of tau into joint velocity, the torque. So some of that.
And del x, what is del x?
Delta x is the displacement, x displacement. So for this work, instead of using velocity as a parameter, we choose the difference in positions. Then that is some called reward engineering. The different works have, or different according to your requirements, you come up with different rewards. So this is not the exact reward that we have used in the latest work. It's a complicated function. Sometimes the reward is a function of true state, but let's say, but planning, when you want to evaluate the cost of the trajectory, you will not have the true state. So the reward function that you have will be like sort of an approximate one, because it is only a function of observations. So all those things are also there. So like contact forces. So generally those are not observable. Like how much is the force acting on, let's say, the base of the robot. So all these things are not known to the agent during deployment. Maybe in simulation you know that, but deployment you don't. So accordingly you have to take that in mind and design the rewards. So all those things are there.
So once we train on simulation, the policy, do we have to fine tune it on hardware?
Yeah, you can do that. Yes, we didn't require it. We made the policy robust to different system parameters like friction, mass changes, etc., link lengths, and we expected it to be directly transferable on the hardware. But sometimes people do focus on fine tuning the policy on the robot. So all that is also there.
I had a question on the reward structure. So these days we see in a lot of the deep RL applications that the reward is pretty customized to the environment. So how generalizable is your reward structure to different terrains? Or is it pretty customized to work on whatever you've tested?
It's generalizable to legate systems. So this same reward function will work on a, let's say, humanoid, similar reward structure. Maybe some extra terms are required to penalize extra motion of these hands and all, so to make it more natural. But apart from that, walking and all, those are some generic terms, like minimizing energy. So that's a generic, mechanical energy is a generic term, right? So all these things are there.
It's extendable to other terrains as well. They're not terrain specific rewards.
No.
Okay. Are there any rewards constraining the spline behavior?
Spline is already, you can constrain it, right, according to your needs.
Does the reward does have it? Is
No, reward is simply.
Is there a constraint in the reward?
No. We didn't work on that. There is one more question.
Excuse me. Does the policy order you have used is pure ANN or did you try this RN and LSTM? Because you can.
So I generally first try simple architectures first. If they work, then that is like sort of a baseline. Then you can improve on top of it. So whatever results that you have showed is with like just simple MLPs.
So far not tried with an RN.
We have tried. So for the vision stuff, we will need that because we want some memory notion of its like of the terrain, right? So some hidden state to encode that. But in this case, it was not required. So kept things simple.
One more thing, while training, you were able to do in CPR, you have used the GPU also.
GPU. So this was not trained in this gym environments that whatever you saw in the previous tutorial. This is a specialized simulator created by NVIDIA where you train like thousands of robots in parallel, collect data in series.
This is transfer learning.
No. So like you spawn multiple robots like 4,000, 6,000 robots simultaneously, collect the data and then do this. And that simulator runs all the physics algorithms on GPU. Collect the data and then use that same data which is lying on the GPU to do your RL updates instead of how. So if you saw these Cartpole environments and all in the previous sessions, they were running that simulator in CPU, then copying the data to GPU. So there is some sort of time wasted there. So and then it is trained. The RL algorithm is trained on GPU. So to reduce that bottleneck, there are some specialized simulators that run everything on GPU. So this is one, NVIDIA IISc.
So roughly how long it took for training?
So it takes around 6 hours, 6 to 7 hours.
Number of episodes?
So I don't know about episodes. So it takes around 200 million samples minimum to get some basic flat ground walking. There was one more question there. Yeah, 6 to 7 hours. And 200 million samples minimum. So this first paper of animal, so not this method, but the first method without all this, so this work was with vision, without all that, it can learn to walk in 20 minutes on that simulator. So, but that is a like very simplistic case. So, yeah. As you have more complex requirements, complex tasks, so training time will obviously increase. But I'm sure that will in the future that won't be a problem. I guess that's it. So, yeah, thank you.
So thanks to Vamshi. Can you repeat your names again? Sorry, I forgot. Lakshmi and
Aditya.
Aditya, Vamshi and Lakshmi. Let's give them a big round of applause. And all three of you please come on the stage, please.
हाँ देखो भी आना है नहीं ऑल बोला मैंने ऑल थ्री ऑफ यू बोला अच्छा हाँ गिर रहा है इधर नीचे
The fourth student was Prakrut, so please come on the stage as well. Please stand up. Let's give them a big round of applause, please. So we have a small token of appreciation for them.
Thank you.
This was the end of today's session. I hope you all got a good flavor of what RL is. in one day I don't think we can teach RL. So our aim was to give you a flavor of the different concepts that are there in RL. I hope you will be motivated and inspired enough to go and study these topics in depth. And from tomorrow, the main workshop will begin. Again, we will start at 9 a.m. in the morning. You can look at the schedule on the RL workshop webpage. Please be on time. And these topics that we will cover from tomorrow onwards will be slightly on the advanced side. But I hope you will, with this introduction, at least you will have a better understanding of what the key contributions will be. So we will end today. So hope to see you tomorrow. Thank you.
Oh, I thought it was like Lotte Choco Pie. I thought it was Lotte Choco Pie.